buck converter. So buck converter is a DC to DC converter. It converts fixed DC voltage into variable DC voltage. Here the duty ratio of the converter is playing the role in controlling the output voltage of the DC to DC converter. So now you look into the circuit diagram of buck boost converter. So here this is the arrangement of buck boost converter, or we are calling it as a buck converter. Here it is a MOSFET and this is the device MOSFET. So here the firing pulse is generated by using this closed loop system or open loop system, and here the pulse for this or duty ratio for this is generated by this PWM pulse generator, and here we have a variable knob to adjust the duty ratio of this buck converter or buck boost converter, and here there is a provision to change the mode of this buck converter. So if the duty ratio of this converter is less than 0.5, that converter will be in the buck mode, and if it is greater than 0.5, the converter is operated in the boost mode. So that is the function of our normal buck converter. And here the output of this converter is negative. So because here we are giving it as a positive and negative terminal, and here this will be the positive and this terminal will be the negative terminal of the output. So whenever you are giving positive input, that converter will give you the negative output voltage. Okay, so here this is the inductor. So this inductor is playing the role in boosting the input voltage. So whenever this switch is turned on, so this connects the input voltages in parallel with this inductor. So the inductor will get the charge from the input voltage. So when this is turned off, so the polarity of the inductor is reversed. So during the charging, this terminal is acted as a positive terminal, and when the switch is turned off, this inductor polarity changes and this will be the negative terminal. So this negative polarity forward bias, and this will be the positive polarity, and it forward bias the diode. So it charges the capacitor connected across this leg. Okay, so after next cycle, again this switch is turned on and this diode is reverse biased, and at that time this capacitor discharges port potential to the load. So this is happening throughout the period of running. Okay, so over here the charging and discharging of the inductor is playing the role in converting the input voltage into less than the input voltage or greater than the input voltage. So now we are going to give the connection for this experiment. So here this is the PWM output pulse. So here the IC is there, and after amplifying this pulse, and it is given, it is available at this terminal, and I am interconnecting the PWM output of the IC PWM pulse generators into the input of or gate of our MOSFET. Okay, then here the feedback loop is taken for controlling the output voltage of this circuit. So I am connecting the feedback wire with the network, and this is the feedback network. So that senses the voltage. So here, and it is given to the PWM pulse generator, and based on the set value it is generating the duty cycle. Okay, so now we can connect the input and output of this converter. So here we need a RPS unit to feed the input voltages to this buck converter. Okay, so here already you know about this RPS. So here we have three knobs, one for the current and another two for the voltage variation, and this is the positive terminal of the RPS, and it is connected with the positive terminal of the buck converter. Then the negative terminal of the battery or negative terminal of the regulated power supply is connected with the negative terminal of the input. Okay, so these two are the input, and here we can vary the input voltages from 0 to 15 volt to analyze the performance and to understand the function of our DC to DC converter. And here I am connecting the meters to measure the input and output voltage. So here I am connecting the positive terminal of the voltmeter to the bottom of the converter output, and here the negative terminal of the voltmeter is connected with the upper part of the converter output, and again I need another two wires to interconnect the meter and the input. So this is the negative terminal of the voltmeter. So it is connected with the input to measure the input voltage of this converter. Okay, so it is connected. So here I connected the voltmeter and firing circuits, then the output of the converters are connected. Then next I am going to connect a CRO to measure the duty ratio of the converter. So basically the output voltage of the converter is depends on the duty ratio. So it is equal to V in by 1 minus D into D. So it is for the Hug converter. So we are going to check the output voltage of this converter, or we are going to validate this experiment by adjusting the duty ratio and measuring the output voltage of this converter circuit for the different value of duty ratio. So for measuring the pulse width or on time and off time of the duty cycle, I am connecting this CRO probe with the gate terminal of the MOSFET. Okay. So these are the two terminals of the CRO, and I am connecting it across the gate and the source terminal of the MOSFET. Okay, in order to measure the on time and off time of the converter unit and the duty cycle of the converter unit. Okay, so here that output voltage is the function of our duty ratio. So here I connected the CRO to measure the duty cycle, and in order to measure the input voltage and output voltage of the converter, I connected a voltmeter in the input, and I connected another meter in the output of this converter. Okay, so now the connection is over. So now we can switch on the power supply, and this is the module, and we can also use the discrete components to make this buck and boost converter. So now in our laboratory we have the trainer kit, so we are using it to validate the Hug converter. And before switch on, we should ensure the zero position of the potentiometer. It is in zero position. So I am turn on the RPS, and I am fixing this at 5 volt. So I am giving input of 5 volt to the circuit. It is exactly at 5 volt, and now I am turn on the kit. Okay, so now I turned on the circuit, and now you can see the variation in the output voltage for the variation in the duty ratio. So now the duty ratio is at minimum position, and now I am increasing the duty ratio of this converter. So there you can see that the output voltage of the converter is proportionately varying with the duty ratio. Okay, so it is boosted the input voltage of 5 volt. So here I fixed 5 volt as the input. The converter output is observed as 10 volt. So it means that the input is 5 volt, the another 5 volt is boosted by this inductor unit. So the total output of the converter is at 10 volt. Okay, so when you are adjusting this duty ratio, so the converter output voltage will vary. Okay, so now I tell you how to measure the duty ratio of this converter. Okay, so we have a cathode ray oscilloscope. So here we should measure the on time and off time of this duty ratio. So this is the on time, this is the on time of the pulse, and this is the off time. Okay, so here the duty ratio is here, then this is the off time, and this is the on time. The duty ratio of this converter can be computed by taking the ratio of T on by the total period. Okay, that means that T on by T on plus T off, that gives you the duty ratio of this converter. Okay, so now you see the variation in the waveform. Okay, so I am adjusting the duty ratio, and here you see that there is a variation in the pulse width. Okay, just you observe the variation in the on time. So here the on time is very low. Okay, so now you see the converter output voltage is 0. Then if you are increasing the on time, you see that now the on time is increasing, then the off time is decreasing. Okay, so this is called as time ratio control. So here I am going to keep the time or time period of the clock pulse as constant, and I am going to vary the on time and off time of the converter unit. Okay, So there you see here, so there is a variation in the duty ratio. So the on time of the converter is varying. So the converter gives the variable output voltage. So actually duty ratio is the ratio between T on by the total time T, or T on plus T off. Okay, so by using this we can find the output voltage of this converter. Okay, and here we can measure the time period of on time and off time. So here you see, and you adjust this. So this is the actual waveform. So a complete cycle. So a complete cycle took two boxes. Okay. So but 2 into 0.1 millisecond. 0.2 milliseconds is the period of a duty ratio, and that one box, that is positive box, covers one box. So here the duty ratio is 0.5 because we have equal T on and T off time. Okay, so when these two are equal, then the duty ratio become 0.5. So this converter is giving the output voltage. Okay, so this is the buck converter, and this is in boost mode, and we can switch this to buck mode also. So here we have a provision to switch over the operation of this buck converter from boost to buck or buck to boost. So now I am shifting this boost operation to buck in order to validate the results. So here you see, so when you are varying the duty ratio, so that can give the output voltage which is less than the input voltage. Okay, so that output voltage of the converter will be less than or equal to the input voltage. That is called as buck mode. Okay, so this is the operation, and this is the, so when you are going to take the readings or recording the values obtained from this converter, so you have to set the values or duty ratio of this converter, and you have to take the output voltage. Okay, so you have to keep this input voltage at constant, or at 5 volt or 10 volt you can keep, and by varying the duty ratio you can observe the output of this converter for the different value of the duty cycle. So that should be tabulated, and that should be compared with the theoretical values obtained from the formula. So that is V out equal to Vn by 1 minus D into D. So that is the formula for finding the output voltage of the buck converter. So by using that formula we can find the output voltages of this converter. Okay, so now I hope that everyone will be clear about this. Okay, so thank you. Next we will see the next experiment.